Hello, everyone. Nice. Yeah, so I'm Han. I'm postdoc at the Hebrew University of Jerusalem, and I'll be talking about the evolutions of the cold gas streams as they enter the hot halo CGMs of the redshift 2 to 3 galaxies. So the massive galaxies at these redshifts usually sit at the node of these cosmic webs, and their growth of the growth of the dark matter halo is dominated by the accretion from these cosmic web filaments. And so the star formations in these galaxies are also detected by how the gas is accreted from these cosmic web filaments, and how those accreted gas are transported to the galaxy at the center of these dark matter halos. Specifically, the massive galaxies at the above 10^12 solar mass halos, at high redshift above 2, are observed to have a high star formation rate. But at the same time, we expect them to be surrounded by the hot halo CGM. There is a critical mass scale, about 7 times 10^11 solar mass, below which you're not supposed to have accretion shock because their Fourier temperature will be around 10^4 to 5 Kelvin, and so they have a fast cooling, and so the shock will collapse, and then there's no hot CGM. But above that, for 10^12 solar mass halos, the Fourier temperature will be about 10^6, so it's inefficient cooling, and so they are supposed to support a hot CGM and accretion shock. You can think of accretion shock as an outermost boundary of these hot halo gas, analogous to the dark matter splashback. Well, so the figure on the right is one such galaxies, and you can see this black line denoting the accretion shock, inside which there's a hot halo gas here. But at the same time, you can also see the cold gas that are coming in along the cosmic web filaments, from the top left and the bottom right. And you can see that they can penetrate deep into these galaxies to reach these centers. So, once you can bring these cold gas from outside to the center, then they can start forming stars, and that's how they can sustain the observed high star formation rate. If you look at the CGM of these galaxies and the observations, you can show these clumpy, dense cold clouds, which can be a site for the efficient star formation rates. And also, people have found Lyman alpha emitting clouds. Specifically, one of these observations, one of these data observations shows the Lyman alpha emitting regions in the filamentary-like structures here. It's also showing a simulated galaxies which show similar filamentary structures where you can see the dense gas coming in along the cosmic web filaments. So here, the main question I'm trying to answer is what will happen as these cold gas comes in, and how does it impact the galaxy formations, and is there any dissipative mechanism that can lead to the emissions of the Lyman alpha that are observed here. So let's look at some of the properties of these cold gas streams in these CGMs. The dense gas streams that are coming in along the filaments can cool very efficiently, and so they'll be have about 4 Kelvin, at the end of the atomic cooling. On the other hand, the dilute gas, the varialized gas halo, does not cool, so they'll have about 6 Kelvin from the shock heating. So if you assume pressure equilibrium, and then this temperature ratio will set also the density ratio. So you can first define the first dimensionless parameter of the ratio of the density in the stream versus the density in the background for a factor of 100. The streams are inflowing with the cosmological inflow, so the velocity will be about Fourier velocity. At the same time, the varialized hot halo gas I will also have a sound speed of about the same Fourier velocity as well. So we expect the stream to be a supersonic with respect to the halo. Again, some factor difference, so like maybe about a factor of 2 difference, so like 0.52. Then because of the density difference or the temperature difference, you can probably deduce that the stream should be a very supersonic with respect to itself. About it. And then another dimensionless parameter is the ratio of the stream radius to the Fourier radius, which you can constrain from your cosmological accretion rate. Give you a bit more details on this. So this previously I was just doing order of magnitude calculations. This is just more detailed predictions. So you can again the delta, the density contrast between the stream and the background. You can predict it as a function of Fourier mass, where the Fourier mass will impact the Fourier temperature. And then once you know the density contrast and the halo density at the Fourier radius, you can calculate what should be the stream density. And then from there, you can also measure the cosmological accretion rate from the simulations or prediction from the EDS cosmology, and based on that, you can calculate this ratio of the stream radius to the Fourier radius. So the for 10 bar 12.5 solar mass, like the density contrast is about 200. The number density of the hydrogen in the streams is about 0.01, and the ratio of the stream radius to the Fourier radius will be about 0.1. Anyway, so based on these numbers, we seek to look at the idealized simulations to see how the cold gas should behave as they penetrate these hot CGM. Well, why are we looking at the idealized simulations? Well, as I explained earlier, the cold gas streams are inflowing with a Mach number of about 1 with respect to the background gas. So when these two fluids shear against each other, we expect them to develop Kelvin-Helmholtz instability. And that is not something that is usually resolved in the cosmological simulations, because to resolve the Kelvin-Helmholtz, you need to resolve these at these scales. And the cosmological simulations do not have that high of a resolution, especially if you are at the Fourier radius when the cold stream first enter this hot halo. So shown here is some samples of the idealized simulations where the Kelvin-Helmholtz instability overtook and the disrupt streams. So they're shown on the left is a adiabatic simulation. So we put in a streams cold gas inflowing into a hot gas background, and you can see that the Kelvin-Helmholtz instability slowly disrupts the streams. It also decelerates the streams over time because it mixes the flowing gas versus the stationary hot background. On the other hand, additional physics can stabilize against these Kelvin-Helmholtz instability. For example, magnetic field and the soft gravity. In the case of soft gravity, which are the middle panel and the right panel here, only suppress the KHI, but when the gravity is strong, then it can cause the collapse and the formation of clumps as well. Another additional effects that can also counteract this Kelvin-Helmholtz instability is radiative cooling. So shown here is a comparison of simulations with no cooling on the left, cooling on the right. To determine what happened in these coolings, we can define another dimensionless parameter, that is the ratio of the cooling time in mixing region versus the stream disruption time. So why mixing region? Well, so what happened is that when the Kelvin-Helmholtz instability mixes the stream gas, that is at 10^4, versus the hot gas, that is at 10^6, it will reach about 10^5 Kelvin inside the mixing layer of the streams. And that means that the gas in the mixing layer can start to cool down and then condense onto the stream. And so if the cooling in the mixing region is fast enough, then it can overtake the stream disruptions. And what you see is that the background keep mixing with the stream gas, condense, cool, and condense onto the streams, and then it repeats. And what you see is that the stream remains dense at all time, and the chemical instability doesn't have time to disrupt the streams. But in both cases, however, the deceleration happened because you're mixing the high kinetic energy, the high velocity gas with the low velocity gas. So, and there's also mass entrainment, and so as the cold gas, as the hot gas cools down, it will join the cold gas, and so the amount of cold gas will increase over time. And when the cooling time is not fast enough, then qualitatively similar to the cooling, although there's a slight suppression of KHI. Okay, that is great, but what I have shown you so far, all of them assumes idealized conditions where I put in a cylindrical streams into a hot background. But we are interested in what happens to the streams as it enters the halo potential. Well, before we go to that, I'm just showing here the mass entrainment, decelerations, the two effects that I described as a function of time here. The dashed line is the predictions from from theory, and the several different lines are the result from the simulations. Initially, the entrainment rate is slower compared to the predictions, but over time, it catches up with the theoretical predictions. The middle panel shows the deceleration, so the velocity decreases. As a function of time, and again, the dashed line is the theoretical predictions, and the qualitatively matches. Another thing that we found is because of the decrease in the kinetic energy as well as the radiative cooling from the mixing layer, we can calculate the net loss of the energy from the gas, and this dissipated energy may be observed as the alignment alpha. Although from here you can see that this is lower than the observed luminosity, about 10^42 arc per second. But again, this is the case when we have no halo potential yet. So we want to know what happened when we put them into the actual galaxies. The first thing we talk about the criterion for the survival. That is the cooling in the mixing layer must be fast enough compared to the stream disruption timescale. We can translate this to the condition on the radius of the streams because the stream disruption timescale is proportional to the sun crossing time, and that is proportional to the radius of the stream. So you can translate that to the critical radius of the streams, arc crit. And so the above this is by arc crit greater than 1, then you will survive. Below this, you will not survive. Again, you can predict the radius of the streams I described earlier from the comparing the cosmology accretion rate versus the stream density, etc. Anyway, so what we find is that at redshift of 2, almost all the streams should be stable. There's more stables even if you go to the higher redshifts. So this is a condition for the survival at the Fourier radius as it first crosses the Fourier shock. Next thing that we'll look into is what happens inside the halo potential. So there are a few things that halo potential do that will change the narrative. So the first thing, the halo potential will cause the stream to accelerate. And this will counteract the deceleration of the streams as I described earlier. Another thing, it will cause the streams to be narrower and narrower. And that means it will have a faster sun crossing, and so then that will lead to faster entrainment. So you see that's the first equation here. Sun crossing is proportional to a radius of the stream as a function of a halo radius. Another thing, it will also increase the density. That means a higher density means higher faster cooling, inversely proportional to the cooling time, and that will also lead to the entrainment rate. So you can parameterize this entrainment rate as a function of a halo radius with some profiles. So this beta parameter is the again how the radius of the streams evolve as a function of halo radius. Beta will be 2 for the conic streams, and if there's a constant density contrast with isothermal halo, but this will be varying for the isothermal streams. Another thing, the dissipative power will also be inversely proportional to the entrainment time scale, because that's the time scale that controls the energy dissipation rates. So once we know this entrainment time scale, we can predict what should be the dissipative power. So shown here is the result from the simulations of the radial mass flux. So we show the mass flux of original stream gas, approximately 1. That means that whatever comes in, we put in at the 1.1 R area goes to the center. But if you look at the cold gas mass flux, it is increasing as a function of halo radius. That means that there's additional flows other than the radial inflow that we put in at the large radii. And this is because of the entrainment of the cooling CGM gas onto the cold streams that I was describing. So what is the implication for the galaxy formations? Well, we'll try to explain this using the bathtub equilibrium model. So the model uses the mass conservation to balance the inflow and outflow of the gas, as well as the formations of stars in the ISM. For example, you can describe change in the gas mass as the gas accreted minus the gas loss that are due to star formations and the feedback. And change in the stellar mass, you can describe as the stellar mass accreted minus plus the in situ star formation. So specifically focusing on the one of these models from the Entrainment 2014, shown here. The lines are the model predictions for the specific star formation rate, fraction of gas, and the stellar to halo mass relations. And you can see that the model predicts a specific star formation rates of the redshift 2 to 3 galaxies, but not at the redshift greater than 5. But the observations at these high redshifts are mainly for the ones that are being compared here are mainly for the halo mass that are below M shock. So they don't have the hot CGM and they have good agreements. But for the low redshifts, or like redshift of 1 to 3, they are for the 10^12 solar mass, and that these can sustain hot CGM, and we see disagreements here. So one way to reconcile this difference is if we can both boost the cold gas accretions onto the galaxies compared to the cosmological accretion rate that is assumed in the model. So here, like if you assume m.m is some factor larger than the cosmological accretion rate, you can compare the specific star formation rate of the latest observations versus the model. It shows that you require about a factor of 2.5 to 3.5 to match the observations, and that is about the same level of increase that we find in the from our model as well. One final point. Showing here the total dissipative energy or the luminosity integrated outside R, again outside the halo radius as a function of this R halo radius. You can see that for certain parameters, then the total emissions, total alignment of emissions can reach above 10^42 arc per second to explain, then that can explain the observed alignment of emissions. So to summarize, if we consider the cooling and the halo potential and the hot CG, the Kelvin-Helmholtz instability can lead to the mixing between the hot CGM gas plus the cold streams, and that will lead to cooling of the gas in this mixing layer onto the cold gas streams, and they will flow along, and then it will increase the cold gas accretion rate onto the galaxies from the cosmological accretion rate by a factor of 2 to 4. Also, the next step is, well, I also described effects of soft gravity and MHD earlier, which are not specifically included when we model this. And so next step will be to see what happens when all of these effects act together. And of course, ultimate goal will be to have cosmological simulations with refinements on streams that can model these effects consistently. Right. Thank you.
Any questions?
Very interesting talk. Thank you. So I recently read some work which looked into the effect of cosmic rays on the stability of cold gas in the CGM. I'm wondering if you could comment on whether or not you're maybe considering including that on the stream stability as well.
That should be included at some point down the line, but I don't think that should be the next step. I think the cosmic ray should have the most interaction with the magnetic field as well, and we haven't finished modeling the magnetic field part. This should be incoming by the work led by Niyamanaka, and so that should be next step after that.
When you look at actual filament reaccretion in cosmological simulation, like it's not really like a cylinder that is falling onto the halo. Like the origin is moving a little bit with time, so essentially you're wiggling a spaghetti as it falls onto the halo. So do you think that in your ideal setup you have some sort of shielding of the gas that is ahead of you that is preventing you from being disrupted? So if I move slightly the halo, there's nothing ahead of it. So would it be changing dramatically your predictions or not? So what's your take on that?
Well, so the Helmholtz instability itself can lead to some wiggling of the streams in these idealized simulations as well. But to answer you, I don't think it should affect too much. In a sense, like most of our predictions were like, it only depends on like some basic parameters like density contrast, the radius of the streams, etc. It doesn't depend on like what will change is that it will change the radial flux slightly, but I don't think it should affect too much on it.
Yeah, nice talk. About 10 years ago, Jeremy Blaiseau and Yoki Rosdahl did cosmological simulations, radiative transfer, cosmological simulations with a refinement on streams. And what they find is that at least for halos, about 10 to the 12 solar masses that you're looking at, these things are free falling into the halo. So the time scale that is relevant here is the free fall time scale. So I'm wondering how the free fall time scale of a 10 to the 12 solar mass halo compares to the time scales that you've described.
Yes, you're correct. So even in these simulations, let me see if I have this plot here. Okay. Never mind. Well, to describe, yes, because of the accelerations of the halo potential, we also found that these streams are almost free falling. And so all of these effects that I described here are under the condition that is let me just go back to the big screen. So the streams have only time from to go from 1.1 R area to 0.1 R area, and so that's all the evolution that you see within this time scale.
Okay, so this is for 10 to the 12 solar mass halo.
Yes,
or something.
This is for 10 to the 12. Yes.
Thank you.
Other questions? So unless I missed it, I feel like you never told us what resolution you want in the streams. What resolution do you want the simulators to reach?
Yes. So for these simulations, low or highest resolution or the smallest resolution length is about 10 to 20 parsecs. So that would be the goal to shoot for.
And since any other questions before I ask another one? So can you explain a little? There is a question. I wanted to hear a little more about the entrainment, how you define. Can you tell us a little bit more what entrainment means in your what you're talking about?
So going back here, so the entrainment is simply so what happened is that the camera hummus, when the camera hummus starts to develop, it mixes the cold gas versus the hot gas, and the cold gas, and so this mixed gas can cool down and joins the cold gas. And so when we said mass entrainment, we are looking at the growth of the total cold gas mass as a function of time, or when we put into the halo potential as a function of halo radius.
Okay. So let me get Corentin to ask.
Can you just go back to your bathtub model slides, because I'm not sure I understood everything. So here you're assuming that. So I guess my question is, like, you assume that the gas, once it reached the disk, is available immediately to form stars, right? Isn't it?
Can you rephrase your question?
So here you assume that once the gas reaches the disk, it can form star immediately. So there's no extra delay due to, I don't know, like, for example, if it's too turbulent and you can't form stars, then there will be a delay or anything.
Yes, there's some parameters in there that controls the star formation timescale versus the disk infall timescale, but I think you're right that except that difference in the timescale that controls the difference in the star formation rate versus the freefall rate. I guess you're right that there's no time delay that we put in there, other than different rates. I guess.
Other questions? So, is there a question? No. I could ask another one if. Is there anybody asking a question online? No. So another simple question. You tell us the streams get narrower when you have a potential.
Yes.
Is there a simple explanation? Well,
so as you go into the halo potential, like, the pressure increases, right? Mm-hmm. And so to counterbalance this increase in the pressure, you need to also increase the pressure inside the streams. And so but the temperature of the stream is constant because of the cooling, and so that the density needs to increase. And then if you increase the density, but you want to also keep the mass flux constant, that means that you need to have a narrower streams.
Okay, thank you. Okay, so if there are no more questions, perhaps the next speaker can set up and we can thank.